Another type of word problem that uses a chart to be more helpful are distance problems. Now, we have learned in previous years or in science or in previous math problems that if we want to find the distance, we multiply the rate times the time. So how fast you're going and for how long are you going. Now there are three types of distance problems, and we will outline these three so that you can tell the difference between them. But in every single distance problem, your chart will be rate times time equals distance, and it doesn't matter if you flip-flop these two, but we always know that the title here will be rate, and this will be time, and this will be distance. Now in the first example, it says bicyclists Brent and Jane started at noon from point 60 kilometers apart. So we know we're talking about Brent and Jane. We know they're 60 kilometers apart. So we'll get back to that 60 kilometers apart and rode towards each other. Now this is the first type of distance problem when they're going towards each other. So let's draw a little picture of what's going on here. Here's Brent, here's Jane. They're going towards each other. Okay? And we know that they are 60 kilometers away from each other. 60 kilometers. So we'll get back to that, but this is the first type when they're going towards each other. And they're meeting at 1:30 p.m. Now, at this moment, we're not going to use that, but Brent's speed is 4 kilometers per hour greater than Jane's speed. So whose speed do we know nothing about? Is it Brent's or Jane's? We know Brent's speed is 40 kilometers more than Jane's. It's Jane's we don't know anything about. So we could call Jane's rate, that's kilometers per hour, that's going to be your rate. Jane's rate, J. And Brent went 4 kilometers greater than Jane. So you take your Jane's rate and add 4 kilometers per hour to that. We do know the time can be tricky, but this time isn't too tricky. They started at noon and they're meeting at 1:30. So they're both starting at the same time at 12 o'clock and they're going to meet at 1:30. So how long is that? That would be 1.5 hours. And they're both riding for the exact same amount of time. So sometimes your times will be the same, sometimes they'll be different. We'll get to that. So we are still going to multiply across. That's exactly the same. So this j plus 4 times 1.5 would give us 1.5j plus 6. And then this would give us 1.5j. Now we know there's one piece of information here that we haven't used yet, and that's that they are 60 kilometers away from each other. So that means if I take Brent's distance and add it to Jane's distance, when they meet up at 1:30, which isn't going to be exactly in the center, that's the thing, is that Brent is going faster. So if we actually fix this, Brent should end up going further, will end up going further, because Jane's not going quite as fast. So we can't assume that their distances are each 30, but we do know that if you add Brent's distance plus Jane's distance, we should get this 60 kilometers. So we're going to add these two distances together. It should equal the 60 kilometers. 1.5j plus 1.5j would be 3j plus 6 should equal 60. We're going to go ahead and solve this. So we subtract 6 from both sides and we get 3j equals 54. Divide by 3 and we get j equals 18. As always, we're going to take that variable and plug it back into the chart and check it before we write our equation. So that means Jane went 18 kilometers per hour. That was her rate. And Brent went 18 plus 4, so he went 22 kilometers per hour. When we plug in the j's here, 1.5 times j plus 6 actually give us 33 kilometers. 1.5 times 18, the j will give us 27 kilometers. 33 plus 27 does equal 60. So we want to check it first before we write our equation, or write our sentence. Now the question says, find their speeds. Speeds and rate, those are the same thing. So here's our rate. we want both of their rates. So Brent rode at 22 kilometers per hour and Jane rode at 18 kilometers per hour. Okay? So that's the first type of a distance problem, when they're going towards each other. And the time isn't too tricky there because we know they leave at noon, they arrive at 1:30. They're both going the same amount of time. So those are a couple things we will have to consider in the next problem. If any of that's confusing, go back and redo the problem and watch the example again if you need it. Example 2 says a helicopter leaves Central Airport and flies north at 180 miles per hour. So we know we're talking about a helicopter. Um, 20 minutes later, a plane. So we got a helicopter and we have a plane. And let's write our formula. Rate times time equals distance. So it's good to get your chart filled out first and then go back and start really reading the question a little bit more closely. I don't try to do it all at once. I try to just get the labels in first and then work on one column at a time. So the helicopter leaves Central Airport and flies north at 180 miles per hour. That's the rate. That's the speed. So the helicopter, we know, is going 180 miles per hour. 20 minutes later, a plane leaves the airport and follows the helicopter at 330 miles per hour. So let's just stick with our rates here. This one is 330 miles per hour. All right, so let's talk about what's going on here. We've got one plane, or the helicopter. Here's the helicopter. It flies north. Now I'm going to do it horizontally, but we'll say this is north over here. Okay. It flies north at 180 kilometers per hour. All right. Now, 20 minutes later, the plane leaves. All right. So let's imagine time is elapsing. The helicopter leaves, and then the plane leaves from the same place, but it's 20 minutes later. So he's going a little faster, but he left later. Okay? The question is how long until the plane overtakes the helicopter? So it's really saying at what point will they be at the same distance? So let's say as this one keeps going, they're going to both be side by side at some point in time. And that's what it's asking. How long, how much time until the plane overtakes the helicopter? So that's what we're working on here. Now, let's talk about time. We know the helicopter leaves at a certain time. We don't know exactly what time, but we know that the plane leaves 20 minutes later. So there's a couple ways that you can do this. This is how I generally do it. First thing we need to consider is that the rates are in miles per hour, which means the time must be in hours. And that's tricky because it says that the plane leaves the airport 20 minutes later. So this is what two things you need to consider. They all have to be in the same unit. So if this is in hours, then this must be in hours. And it's easier to change this to hours than change these rates to minutes. So that's the first thing. The second thing we need to consider is who has the least amount of time. So what I do is usually the object that leaves later, the least amount of time, because they leave 20 minutes later, they have less time. I call that one X because they have less time. Then the helicopter we know has more time because it leaves 20 minutes earlier. But we have to convert that 20 minutes to hours. So 20 minutes out of 60 total minutes in a single hour, we have to figure out what fraction of an hour that actually is. So 20 minutes out of 60 total minutes in an hour, we can cancel the zeros, and 2 over 6 reduces to 1/3. So 20 minutes is 1/3 of an hour. So the plane has X amount of time. The helicopter actually has a third of an hour longer. So he has the same amount of time the plane has plus another 20 minutes or another 1/3 of an hour. So that's the hardest part really, is knowing that you have to convert this minutes to hours here, and we want to give the time to the shortest. Give the variable to the shortest, the one that has less time, and then the other one you add to it. Now this example is an example of two things going the same direction. The last one, they were coming towards each other. These are going the same direction. Now, if they're going the same direction, we'll talk about what that means for us later. But we're going to go ahead and multiply across here. 180 times x is 180x. 180 times a third is 60. So nice for us that that fraction does drop out, so we don't have to worry about that later. And 330 times x is just 330x. That's a plus. All right, now, here's the thing. We want to know when the plane and helicopter are side by side, and at that point the plane's going to start taking over the helicopter. So that means if they both left from the same place and they're both ending up side by side, what do we know about their distances? The distance of the helicopter and the distance of the plane. They have to go the same distance for them to eventually end up next to each other. So when you're doing a problem when they're going the same direction, then what we know that they're going to have the same distance. So we set the distances equal. Running out of space here. So here's the distance of the helicopter and the distance of the plane. Those better be equal if the plane is coming up right next to the helicopter. So we're going to set these two equal to each other. So our equation should be 18x plus 60 equals 330x. And we solve that then. Subtract the 18x. 60 equals 150x. Wait a second. Oh, this is supposed to be 180. 180x. 180x. There we go. That does give you 150x. Sorry about that. 180 times x would be 180x. Then we divide both sides by 150. Now it's okay that this is happening. We get x equals 60 over 150. Let's reduce this. So what number can we divide 6 and 15 by? We can divide them both by 3. So we get 2/5 of an hour. Okay. Now this is 2/5 of an hour. That's the time. We want to probably figure out how many minutes that is. Okay. So 2/5 of an hour equals how many minutes out of 60 total minutes? So we're going to use a proportion to solve this one. There's a couple different ways you could do this. So if we know that we have 2/5, then we want how many minutes out of a total 60 minutes. So we can cross multiply. We get 120 equals 5x, and x then would give us 24 minutes. Okay. The other way you can do this is actually figure out what 2/5 is as a decimal. It's going to be 0.4. And then you can just multiply that by 60 minutes. And that's going to give you exactly the same answer, 24. So there are two ways you can consider doing that. Now, if we want to check our answers here, the checking gets to be a little more confusing. You have to use the original x, 2/5 x. So this is where this gets a little more challenging. So x would be 2/5. Now let's just go ahead and do the distances. 330 times 2/5. So 330 times 2 divided by 5 gives us a distance of 132. Now 180 times 2 divided by 5 would give us 72 plus 60 is going to give us 132 also. So this is, of course, going to be the most challenging piece, but if we don't need that to answer the question here, then let's just make sure the distances come out to be equal. Okay? So we do know that they come out to be equal, so we're good to go. The question is, how long until the plane overtakes the helicopter? It will take 24 minutes before the plane overtakes the helicopter. Okay, so if example 1, they're going towards each other, then you add to get a total distance. All right. If they're going the same direction, then they have to end up going the same distance. So you set their distances equal to each other. So those are the first 2 types. The other thing, remember the most challenging piece here was that we had to convert the time into hours. Okay. And the last type, example 3, a ski lift carried Maria up a slope at a rate of 6 kilometers per hour, and she skied back down at 34 kilometers per hour. So what is Maria doing? She's skiing up. She's taking the lift up. Lift up, ski down. All right? So she's going to take the lift up, and then she's going to ski back down. Okay. Rate times time equals distance. So let's fill in the easy stuff. The ski lift carried Maria up a slope at 6 kilometers per hour. 6 kilometers per hour, which means the time must be in hours. And she skied back down at 34 kilometers per hour. The round trip took 30 minutes. All right, so with a couple challenging pieces here. Let's first talk about the difference between this setup and the other 2. This one is what we call a round trip. You go one distance at a certain rate, you come back at a different rate. Now, in order for this to work out, we're assuming that we know people ski back and forth, but we're talking about her overall distance, not the actual distance she's going back and forth, but the distance from the top of the hill to the bottom of the hill. Okay, so we're assuming a straight path here. Now, we know that the total distance took 30 minutes. So here's one of those totals again. When we go back to the coins, if we knew we had 54 coins, then one of them was X, and one of them was the total minus X. We know we have 30 minutes. That means that one of them is going to have to be X, and one will have to be something minus X. You have to be careful here. Now the question says, how far and how long did she ski? So the skiing is the big question here. So let's call ski X. So here's the thing. If we know that it took 30 minutes for the entire round trip, we know it's not 15 up and 15 down because she's going much slower up. So this is going to take a lot more time to go up because she's only going 6 kilometers up and 34 kilometers down. So it's not half and half. It's not 15 and 15. Before we do anything else, we do have to remember that we have to convert this to hours. So 30 minutes out of 60 minutes is, of course, a half an hour. So we know that the total of the lift and the ski time should be a half an hour, just like this. If the total is a half an hour, then one of them is X, and one of them is 1/2 minus X. It's always the total minus X, not X minus the total. That is the trickiest part in this entire problem because you have to convert it to hours and you have to deal with this whole total scenario that we keep seeing. Now, the rest is actually not very challenging. We've got to multiply across, so 6 times 1/2 is 3, minus 6 times X, which is 6X. Multiply across here, we get 34X. Now, the question is, it's a round trip. What do we know about the distances? Going up to the top, coming back down. The distances should be the same. Set the distances equal So the distance for the lift should be the same as the distance skiing down. So we set 3 minus 6x equal to 34x. Add 6x to both sides, and we get 3 equals 40x. Divide by 40, and we get x equals 3/40. Now remember, you can just do 3 divided by 40, which is going to give us 0.075, okay? Now, take that 0.075 and multiply it by 60 minutes. And that will give us how many minutes? 4.5 minutes. Okay? However, when you are checking your answers, oops, I'm sorry. There we go. So 3 divided by 40 is 0.075. Then if that's the hours, we take the hours and multiply by 60 minutes, and that will tell us exactly how many minutes. When you go back to plug this in to check your distances, though, make sure you're using this value, not the minutes, but you have to use this. So when we do 3 minus 6 times 0.075, we get 2.55 kilometers. And 34 times 0.075 will also give you 2.55 kilometers. So she skis, she takes the lift up, she skis down. Those distances should be exactly the same, and they are. These again will be more challenging. So just go ahead and check your distances on these to make sure they're right, and then you can answer the question. How far and how long did she ski? Maria skied for time 4.5 minutes. And so that's how long, and we know how far. And she traveled 2.55 kilometers. Okay? So the 3 types of distance problems. They're going towards each other, then you should add their 2 distances to get that total. If they're going the same direction, then they have to go the same distance also. So you know that you're going to set the distance equal to each other. And finally, if it's a round trip, then the distances should also be equal to each other, because you're going up and down, or even if you're going east and west, if it's anytime it's a round trip, the distances should always be equal. So there's your distance, rate times time problems, word problems.